Ladies and gentlemen, we will start. We have joined two sessions now, session 2A, where we have two speakers which had to apologize that they cannot take part for several reasons. And so we decided here a small audience, and I think we have a very interesting presentation from session 2A concerning wave modeling from the Hellenic Naval Academy. And my name is Hans-Dieter Ehrenberg. I will chair the session together with my colleague in the technical committee from CTM in Poland. Your name is?
My name is Rafał Domioczko. I'm from Poland, from CTM.
Yeah. And we'll start with our session and then we will take over. So I will shortly introduce you. Our speaker is not the speaker or organizer. He will introduce the speaker of the main subject. Professor George Galanis, he's the director of the section of mathematics of the Hellenic Naval Academy and the head of the mathematical modeling and application laboratory, as well as the deputy director of the postgraduate program Marine Science and Technology Management, jointly organized by the Hellenic Naval Academy and the University of Piraeus. He's also visiting professor of the US Naval Postgraduate School. His research activities focus on the fields of mathematical modeling and information geometry with applications to optimization, wave modeling, and marine meteorology, data assimilation, and stochastic calculus. So we are looking forward to your presentation and of your student.
Thank you very much. Thank you very much, Mr. Chairman, dear colleagues. Ladies and gentlemen, thank you very much for being here today. It is my great pleasure to introduce you a recent work that has been carried out within the framework of the Mast program in Marine Science Technology Management. This is a relatively new program that we run as Hellenic Naval Academy jointly with the Maritime Department of the University of Piraeus, in a scheme where the two biggest universities of Greece in the areas of naval and maritime sciences are met. The main goal of the program, and this is something that I hope that you can see in our work in our presentation too, is to introduce the technological component in maritime and naval studies. Supporting graduates that will work or are already working in the Hellenic Navy or in the maritime industry. So, within this framework, Mr. Giorgos Stavris, who is a graduate of the MSc program, and we try to employ numerical wave models for providing vital information to naval operations. Wave modeling provides today a very good alternative to observations that we do not have over sea areas, since in most of the cases a dense monitoring system is not present. So state-of-the-art numerical models are available today in which the physics of waves evolution are fully parameterized. This is the wave system, the wave modeling system that we use. The one system, the one model, a third generation 2D spectral wave model, which describes the evolution of ocean wave spectrum, of the two-dimensional ocean wave spectrum, with a source function that includes wind input and wind forcing, the most important parameter, but also a number of procedures and issues that one should take into account in wave modeling, like nonlinear transfer between waves, white capping, dissipation, and so on. The wave modeling system that we have set up at the Hellenic Naval Academy covers in a high spatial and temporal resolution the area of the Eastern Mediterranean Sea, with domains, nested domains focusing in areas of interest, as you can see in the slide here, and also exploiting any available other information like observation for buoys or satellites, and a statistical optimization scheme based mainly on Kolmogorov, Zorpenko, and Kalman filters for the elimination of any possible biases. We ran with our colleagues in the US Naval Postgraduate School a similar model in a domain with different, of course, wave characteristics in the North Pacific Ocean, focusing in an ST domain on the west coast of the US. As already mentioned, we use advanced statistical and mathematical techniques here to adjust the results of the model to local conditions, mainly based on Kalman filters, but also to other type of statistical procedures like KZ filters for removing high frequency or unnecessary variation from the initial data. I'm not going to be more technical, George will do so, but what we are trying to do finally, the information that we are trying to obtain finally here is to define, I mean, in this work, is to obtain information on weather windows, on time, let's say, intervals that allow or not an operation that we have to take. So if we have some specific, some predefined thresholds for the operation or for the ship that we are going to employ, we can use wave modeling to obtain such information, such weather windows information a day or two before the operation, which is important for decision making and for the planning of the operation. So here I would like to ask Mr. George Stavris, a graduate of our MSc program, to take the floor and give us the details, the technical information for the study. George.
Good afternoon. This work has been carried out with Professor George Velanis, as aforementioned, the framework of the MSc program Marine Science and Technology Management, jointly organized by the Hellenic Naval Academy and the University of Piraeus. The duration of the presentation will be approximately 20 minutes. Here we can see the presentation outline. The purpose of the presentation is a presentation of the basic characteristics of marine waves, highlighting the utility of wave modeling, showing the main models and how they can be used operationally by the Navy. From the first activities of man at sea, the phenomenon of waves particularly occupies me. Waves have influenced and influence sea travel decisively, and therefore, the development of models to determine and study its major achievements. The sea wave, like any other waves, is sinusoidal disturbance of space with specific wavelength and amplitude, which spreads in all directions, releasing energy. It's worth noting that in the sea waves there is no displacement of water mass, but only a change in the shape of the sea surface as a result of the winds. Waves are also created by release of energy in the ocean, either from space, and we have the interval waves, or from tsunamis, tides, and even from human intervention. We will be concerned with two categories of sea waves: wind-generated waves and swell waves. Wind waves. They are created when the wind passing over the surface of the sea exerts pressure and at the same time turbulence, which results in the generation of V-shaped circular waves. This in turn creates a more turbulent surface, which allows the winds to continuously transfer energy, starting the creation of gravity waves, which have symmetrical shape. The more energy imparted to the waves, the greater their height, wavelength, and speed. They get maximum speed, height, and wavelength when its speed equals that of the wind, at which point energy transfer stops. It's pointed out that the energy received by such a wave depends on the intensity, the period of time it moves, and finally the distance at which the wind blows for a period of time. Swell waves. These are created by the wind waves that have received such an energy that they continue to propagate away from the point of creation. These waves differ both in their direction and its wavelength. When the wind stops, they become symmetrical, acquire a speed greater than that of the wind, and a long wavelength, resulting in a decrease in height. In essence, potential energy is converted into kinetic energy. The phenomenon is observed that the waves with longer wavelength travel faster, and that many smaller ones move in between them. One of the greatest dangers in navigation is the contribution of swell waves from different storms, as the contribution causes either the amplification or damping. Sea waves and energy. During the propagation of a swell wave, the energy loss is very small. A wave begins to have significant energy losses when the depth decreases to such an extent that it is less than half the wavelength. Then the kinetic energy is converted into heat. The study of energy is done through the understanding of the energy spectrum of the wave, and a set of parameters is used such as wavelength, L, period of time T, frequency F, wave height H, propagation, velocity, and incline. Categories of numerical models. A very convenient way or approach for the study of sea waves today is that of numerical modeling. These are three main categories of numerical models: the limited area models, which are restricted medium-scale areas of interest, the global models, which cover the entire planet, and computational fluid dynamics, which are simulation of smaller or larger scale, mainly around infrastructures and the design of aircraft and ships. In our study, the numerical model adopted was the one model utilized today by a wide number of operational and research centers. The most significant data entered into the system before processing are a coordinated system, the bathymetry, the presence or absence of depth or current refraction, temporal effect of wind, and the nest grid. The one-wave model is a third-generation model according to which the wave spectrum is calculated by integrating the energy balance equation without any prior constraint on the spectral shape and can work effectively for both shallow and deep water. Using this model, the following are calculated. We can calculate the maximum expected wave height, significant wave height and direction, wave mean direction and frequency, height and mean direction of the swell wave, and the full wave energy spectrum. One model at Hellenic Naval Academy analyzes the data through the use of very high spatial 5 kilometers and temporal 1 hour resolution. We have a simulation of observation from buoys and satellites, and finally statistical optimization and local adaptation processes. GLAM is a third generation 2D spectral wave model that describes the evolution of a two-dimensional ocean wave spectrum. Here we can see the equation. And after that, the source function is called S, includes the wind input SC, white caping dissipation as this, and non-linear transfer SNL. The one mathematical model does not use assumptions in the spectral scene, but integrating the transfer equation shown in the previous slide, the two-dimensional fluctuation spectrum of the wave variations is calculated. If one looks back into the national literature, he can or she can identify cases over time where the correct and respectively incorrect use of environmental conditions have decided the fate of not only the ship's crew but also the whole world. A typical example is this, perhaps the Allied invasion of Normandy in 2000 in World War II. Naval operations and missions are divided into the following three categories. We have the dominance of surface and subsurface, the cold ACW warfare, air supremacy, and the power projection. The wave significantly affects the performance of weapons, electronics, and marine systems. Sonar of surface units make difficult the localization of submarines. This happens as the sea layers mix and create noise and rapid fluctuations in water temperatures. Wave and wind also affect the operations of helicopters, as the takeoff and landing on deck requires the fulfillment of strict conditions and that the manufacturers specifies for each aircraft or helicopter. The wind affects the range of action of guided projectiles and the accuracy of the shot. Finally, The wave affects the SAR operations, tertiary rescue operations, special naval and amphibious operations, and seismic surveys. As it can be seen in the projected slide, this model offers high spatial and temporal resolution. Through the appropriate software, the one model can provide the Navy with a daily forecast of wind and sea waves for its area of interest, both in the Mediterranean Sea and in the wider Greek area. It's installed at the Hellenic Naval Academy and provides data for use in various operational activities. Suppose we want to plan the conduct of an amphibious and landing operation on an island in the North Aegean Sea. The study will be carried out in 3 phases. The first one will be done in total for the years 2020 and 2021. The second phase is about the winter months of 2020 to 2021. And at the phase 3, we will select the 5-day period to examine if our ships can be operative or not. The data about the year, date, and time will be related to the values shown in the projected slides. As we can see in this slide, we indicatively set a maximum wave height for small inflatable speedboats to be operational at 1.5 meters, and the maximum wave height for landing ships and hovercrafts to be operational at 3 meters. The maximum permittable wind intensity is 20 knots for the small inflatable boats and 30 knots for landing ships and hovercrafts. First phase, by choosing the appropriate combination of latitude and longitude, the following positive results are obtained for the period of 4 months to 2020 and 2021. Here we can see that for the small ships at northern part, the percent to be positive is 90.82% and 88.82% for land ships and hover ships on the northern part. And the southern part, for the small ships, we can see the percent 90.66% and 98.8% for the land ships. In the next slide, we can see the results for phase 2. The small ships can be operational at the percentage 57.20% at the northern part, and the land ships and hover ships can be operative at the percent 63.51%. At the southern part, on the other hand, the percentage is 57.11% for small ships and 61.32% for the land ships and hover ships. Firstly, it's assumed that the execution of the operation on the island of the North Aegean Sea will take place from 6th to 11th January of 2021. Having a wealth of data available on the wave and wind conditions in the area, the military leadership must decide when and where it's best to conduct the operation. From the results of phase 1 and phase 2, it appears that the best weather conditions are in the northern part of the island, and the disembarkation of the special forces is planned to be carried out using small boats. We have one more parameter that the land to the closing of the naval force, the manning of the boats, and the execution of the operation is about 4 hours. In the following diagram for the entire 144-hour period, and then in the following 6 diagrams per 24-hour period, blue indicates when the operation can be carried out, yellow indicates the prohibiting conditions, and the red the prohibiting conditions. The minimum time for the approach, as mentioned for the naval force in the northern part of the island, the manning of the fast boats, the clearing and the landing of the forces on board is set 4 hours. According to the analysis of the simulation model, the situation from 6th to 11th January evolves as shown in the respective slides by day. At this slide, we can see the 6th and 7th of January, 8th and 9th of January, 10th and 11th of January. The study of the above diagram shows 3 large favorable time windows, one marginally short of the order of 5 to 4 hours, and one at the end of the 144 hours. The first is between 0602 00 to 070700 local time, and it's a 29-hour window. The second is between 071700 to 081000 local time, and it's a 15-hour window. The third is between 090100 to 090400 local time, and it's a 4-time window. The fourth is between 091400 to 110600 local time, and it's a 38-time window. And finally, the fifth one is between 111300 to 112359 local time, and it's 11 hours window. From the diagram shown, it's appears that the most favorable period for the operation is the 15-hour window between 07 and 08 January, as since there is a red window before and after, and so the enemy won't have the ability to transport its reinforcements with small and fast boats. Finally, the following general table emerges. For the 6 days period, the small boats can be operated at the percentage of 78.83% and non-operatable at the 21.17%. Conclusion. Climate, global warming, and the question about the climate change are creating changing maritime conditions that have a catalytic effect on the protection of navigation. The wave is the result of wind, movement of liquids of different densities, energy release, and human intervention. At an operational level, sea state must be taken seriously as it affects both the ship and its personnel. The degree of influence is inversely proportional to the size of the ship. Similarly, wave and wind affect submarine, helicopter operations, search and rescue operations, and other type of surveys. Numerical wave models provide today a great alternative of local observation. At this moment, I conclude my presentation, and I'm at your disposal for any questions.
Thank you, sir. Any questions, please?
Yes. I am Ioannis Rekas from Flight and Space magazine. Have you taken, you might have said it, but I probably missed it. Have you taken a specific model of the small boats from the special forces? For example, the typical of the Greek army?
These parameters, it's set by myself, but it's close to the truth. They're not the limits of a small inflatable boat.
Probably is a type of rib, for example, 10 meters.
When I say small inflatable boat, I mean it's something like a rib class, but probably the true limitations are smaller or higher.
So it's the average of a typical.
Yes, I took an average limit, and took a certain geographical area from an island in the northern Aegean Sea. And with the data I collected with my professor from using the one-wave model we have in Hellenic Naval Academy, we filter this data, and we have these percentages I show you in my presentation.
Thank you very much.
But you can adjust, sorry for just
Yes, of course.
Just a few words more. You can adjust this study to the area and to the limits that you are interested in. Okay, so what we do with George, and as an academic institution, of course, is to provide the method, to provide the tools. The application is on the user.
Great, I understand. So probably if I want to extract the data I need for, so if I use, for example, a node read, I add the parameters in the system, it gives me a specific conclusion. Okay.
Exactly.
Thank you very much.
Any more questions? Sarah?
Anna Kudulakis from the Hellenic Summer Association. So, can you merge real data into the system in real time using all the movies from Poseidon, whatever system we have or we are going to have, in order to validate the model in a feedback mode to provide in the next 24 hours in more realistic formats?
We have the data for many years, and so we can predict for I think it's for a 7-day period, if I'm not mistaken.
So I'm asking this question because, as you know, NATO always we have these big databases of last years, etc., etc. Due to the climate change, all these things are not very well validated anymore, let me say. We see new things, new formations of hurricanes in the Mediterranean. So the statistical data of the last years, really, they don't matter so much. So when we discuss about real-time environmental picture, we discuss that we have some of them can give us data yesterday and the day before, and we can make a model for tomorrow. So how you can connect the system to a real live feedback? This is my real critical question.
You know, in fact, the wave model that we use, but also most of the state-of-the-art current wave models simulate all the physical parameters and all the physics in general of waves and wind, and give you the situation as it is now, or as they forecast it for the next 24 or 48 hours or whatever. It's not just a statistical estimation. Okay, it's what we expect for tomorrow.
Yeah, that I'm getting feedback from today's data.
Yeah, this is what we are trying to do with the optimization methods that I mentioned, carbon filters mainly, where we have statistical methods for identifying and decoding the error of the models in the specific area of interest, and then try to improve the next forecast. So
Because as I say, not always I'm watching the weather, and always I'm getting the wet, because it never is the weather that they predict.
So this.
Yeah. Okay, thank you. Very good.
And to finish this, these wave models are used to predict, to give information for seafarers to say, okay, you will have to expect these and such waves in a certain area. Would that be the goal of this wave modeling, or what is the main purpose of it?
Again, it depends on the user. I mean, we as a research and academic institute, we are mainly interested on the assimilation methods or the post-process methods that will make this model more accurate.
Yeah.
But for a user, for a sailor, for the Navy, what makes sense is the result, is to have accurate information for the specific operation they want to do, and not a general, you know, it's easy to have the general situation, to have a forecast, a good forecast for the general situation. What is difficult to do is to have specific information for parameters that you are interested in, would be significant waveguide or period or whatever, at a very local area. So these are the challenges.
Yeah, and so you are in principle able to protect, make a prognosis for a certain area.
Yeah.
If the wind is blowing, let's say 4 days in a certain strength,
Yeah.
then you are able to say in that area we will have waves of that shape and that height.
Yeah. Yeah.
And you do the landing or not?
Yeah, yeah. Okay.
Thank you.
I will now hand over to you. We will continue with session 2B with the other presentations.
Okay, our next joint session is Future Maritime Technologies Success. The next project is Mr. Nathan Fournier with the presentation Data Mooring and Innovating Solution to Extend Ranges in Data Rate. Nathan is from France. Nathan works in Technical University Bretagne, and on this university he is working on PhD title. Nathan, the floor is yours.
Thank you. Okay, it's a pleasure to present my works. It's actually a work in progress. You will see there is a lot of things to do yet. I hope that some days there will be a data milling solution that is running for technical operation. Before moving to the data milling subject and why it's an innovative system to extend ranges and data rates. I just want to give a word on the lab where I'm from. So it's in France, it's the West. So it's in the West, so it's a lab around our region in a lot of engineering school and some university. And especially, I'm part of the robotics team. We are doing robotics for exploration, and what our main subject is interval analysis and abstract interpretation. So I will not talk about this because it's, I think, way too technical for today. But it's useful tools to guarantee area, guarantee part of a robot. So if you want a word, you can take a look at our website and talk with my advisors and professors that are well known in the interval analysis. So, our subject. Why do we need a thing named data mirroring? First, maybe this scheme can be familiar to you if you do some underwater research for Army. So maybe we want to find a target which is underwater. So we launch an AUV to scan all the zone. But that's how the timeline is. You launch the AUV, like maybe 8 hours, 10 hours, one day, and you recover data, and then you analyze data, and then you do the mission report. What if can we add a piece that named data mirroring? This is for history naming, it is called data mirroring, to recover data, but before the end of the mission, and recover data all along the mission. Why are we looking at some stuff? Because in underwater world, we can have few underwater wireless interfaces, but we can choose optical ones. So it's a really great data rate, but it's a low range solution and gives a lot of technical operation issues as alignment of emitter and transmitter. So it can be hard for long range. Maybe we can rely on acoustic, but the main problem in acoustic is not the range, it's good, but it's data rate. How can we transmit video through acoustic? It's impossible. And the next one is radio frequency that are not in the optical thing. Actually, they said that we can reach 10,000 kilometers, but in literature we will never find this. It's few centimeters, like a meter for some frequencies. So it's not a reliable solution to do long-range transmission. And to show some maybe value, if we want to transmit with acoustic waves, 1 gigabyte over 300 meters, it's 7.4 hours. What if we can add something here to use optic or radio frequency? Because over 300 meters is not possible for optical. That's how came data mirroring. So here's an example. Let's say that the source is the point where data are collected. Like for now it's static, but maybe we can think of moving sources, like an AUV. Some robots that can move to reach region named D, where D is a short distance that we can have a high bandwidth transmission. So, and the way to carry data from the source to the destination. Is it good system? Is it a good idea? Well, is it a good one? But let's see it during the presentation. First, to do some history and a bit of literature. Data muling is not a new word. It's not a new word. It had called in 2003 for terrestrial thing, and it's basically the use of a mobile agent to physically transport data. One of major example is mailman or post system to carry mail from post to mailbox. And so the characteristic of mules, the two characteristics, is that they have a short-range communication system, and in underwater world and as in surface world too, it's basically always high bandwidth and a capacity to move, so to reach communication zone. Don't be afraid of all the question. If you want to take a picture, you can to find where they're from. But basically, it's the time of latency. It's the time to carry one amount of data from A to B, and the amount of data is named M here. The TCOM is the communication time. If I want to communicate from A to this zone here, it's TCOM. And T travel is the travel time of a mule over this zone. So if we divide the zone A to B in small zone for mule, the T travel is to go from this point to this other point. And basically we can express so the time to transport one packet from A to B, the total time to transport an amount of P packet from A to B, and this is the expression of communication time, the amount of data, B is the data rate. We add a term of wave propagation, so we will neglect this because sometimes the celerity of the canal is way bigger than the travel distance. It's not true in acoustic in underwater world, but if we will look at optical system, so it's true. We can neglect this term, and the travel time is the distance over the speed. And we will see what is the apparent data rate from A to B for our link. Before giving some numbers and values, a small talk, like if we rewrite the equation, we can have a criteria that tell us if it's better to have a lot of news or the less number of news. So we'll go through after. Okay, let's take some value to take a hand of what I'm talking about. So I took underwater optical communication system. It's underwater system, so 27.1 megabytes is okay. It's if we call it our graph, it's inside the zone. I took the distance of 300 meters for the global distance, and for transmission distance, it's 10 meters. And RDV, it's time to rendezvous. It's the time that we can consider to zero if mule can gather without losing time, or maybe consider more time if they have to reach, to align, to do a better communication. And that's what we see on the right graph. We achieve some pretty interesting data rates. It's 12 megabytes or 8 megabytes for considering 100 seconds of rendezvous. And if we recall, acoustic link was around 30 kilobytes out. And you can achieve a bit more, but not so much. But is it enough to say that it's an innovative solution and that we can extend ranges? I think no. It's good, but it's not an operational system yet. Because if we look, we can say, oh yes, if I augment the size of the packet, it's better, okay. But the less my packet size is, the more I need to travel and to move from A to B. So we need to consider energy of underwater systems. And for ranges, yes, it's decreasing around the ranges, but if we consider 8 kilometers of communication with maybe 9 or 10 mules, it's okay, it's still better than acoustic link. So why can't consider this? And to give an idea with transfer time, because sometimes data rate it's not really handy to consider. So let's say for 9 gigabytes, it's around 2 hours. If we see this in this graph with with 10 years and a distance of 300 meters. So it can be achievable. How to implement this? Because that's equation, it's good, but it's not operational, and that's where the problems arise. We can consider a bit scenario that that will be my scenario for my experimentation during the November month. Because when we consider the mule, which communication do we choose? Which speed? What is the amount of energy? What is the autonomy of the system? And I think the main challenge is how to perform rendezvous. How to know that the two mules will be around this point to communicate. How to guarantee this? We saw that with GPS, it can be denied, jammed, spoofed. So maybe we have to explore other way. That's why it's still a work in progress. I'm in this step. I look for if in literature it exists, some things, or if we need to build one from scratch. And to understand how a mule works, I drew a small state machine. So the mule is in the way to receive. She waits here to receive data. When she has all the data, she can move to the other point. She's going forward. She is now in way to transmit, and then she can go back when she transmitted. It transmitted all the data. We can have some link in between. Maybe here we are still in ranges, so we can start to communicate to optimize the system. And to experiment this at Instable time, we have a fleet of small DD boats. It can not operate during strong wind or on sea, but it's practical because we have 20 of this. So it's the same, and it's a differential drive with two helix. We've got an IMU and a GPS, so it's a good way to start experimenting. I will do a vector field navigation. Don't worry if you don't know what is it. And for communication, I will consider further a Wi-Fi connection because doing this underwater, it's yet still too high. So we want to experiment the concept a bit before on lake and surface. So to conclude, yes, I think I showed that it can extend the ranges, extend the data rates, have application in underwater world or surface or terrestrial. But the operational system need to be built. So there is few programs that exist already, and some with it's not the good reference, sorry, but some Portuguese team. The Portuguese team work on the system. It's not like mine with linear. It's more secure, but they are still have a demonstrator in underwater mode, so that's a good way to start. And this is, I think, three of the main issues to build an operational system as I presented. I had the launch and recover system because it's an issue, even with its 4 small boats, it's an issue to put all 4 inside the lake. So what it will be if we have hundreds of robots? What if one node fail? How they can act? So that's all. Thank you for listening. If you have a question.
Do you have any question? Our president? Yes?
You showed the models that you are testing, the small boats.
The small boats, yes.
First of all, how big is this?
It's this big.
Okay.
So it's really small boats. We use it on lake, and it's used as an experimental platform for researcher and PhD students, but it's also took part in the teaching field. So students help us to improve the capacity of these small robots.
And I guess then the purpose is for the next step to test on underwater
Yes.
small vehicles, right?
Yes, we are trying to build one at the same time, but it's not yet operational to do what we want to do. That's why we have to build it.
Thank you.
Yes?
It works only for linear data. I noticed in the last slide on the conclusions.
So for linear data, it works. Like on paper, it works.
Yeah.
We need to do it.
For
Operational
non-linear?
one.
For non-linear?
No, it's linear there's no link with non-linear. No. It's just to different it from the circular one that is presented by the Portuguese team.
Okay.
But maybe we can try to find non-linear one.
So yeah, it's
If you have ideas.
so it's something that needs some more work or more research to decide on.
Yeah.
On it. Okay.
Thank you for the clue.
Any question? Okay, thank you for a very interesting presentation. Now we are finished our session. We can. Maybe we do a photo for presenters.
Yeah,
Sure.
Yeah.
Okay.
Mr. Professor. Yeah, of course.
Oh, maybe we can post that.
Yes, the Mast is
Maybe, yeah. Not on this lamp.
Okay. Thank you.
Is it possible to take one, or can you send me the picture?
Of course.